Thank you very much, Professor Nazaruddin. Thank you all the colleagues, Professor Yusuf Jazz for organizing the conference. And for the last 3 years, we are following it due to pandemic situation. This year, we will not able to attend in person in a 3-dimensional, but let's say 2-dimensional is we are doing it. And all the participants, I can say more than 125 who are attending in and wake up so early. Our colleague Jamping Ki is maybe some technical issues. He is an excellent organic chemist and work on organic solar cells. He was not able to do that. So I will be doing the first talk today of solar cells. Thank you very much. We work on 3rd generation solar cells emerging. And for the last 2 days, I have listened a great line of a speaker on the conference in the IRSEC conference on battery. So energy storage and energy generation, both are very, very important for our planet, apart from, of course, health, which we are struggling now. And they were fantastic speaker, a line of a speaker, and they were the frontline researchers doing research on the battery here. Today, I will talk about some of our recent results because I am pretty sure you will hear a very fine, good perspective from Professor Nazaruddin. Nazir is a front researcher in perovskite solar cells. So I will just go quickly in some of our results recently we have been doing with the passivation approach to increase the cell performance and other type of things like we do that in mitigating 2D-dimensional losses. Today, our planet is going in an unprecedented time. This unprecedented time needs unprecedented solutions. It's not like today we have problems with vaccines, but in the meantime, we also need carbon-free energy, and this carbon-free energy should come from many sources: winds, energy storage, energy generations. So this is a very fine picture I find this month in the Time magazine. This was I took the liberty to take it. So we need things, and vaccine and renewables are equally important because we don't want to repeat the scenario of global warming of much more than that. So ladies and gentlemen, this is the picture across the globe in the month of August. There was a very big fire in San Francisco, you can see that. In the meantime, there were somewhere droughts. The glaciers were melting and some countries were under the flood. So this is all the picture in the August, only in 1 month across the globe, different scenario. So we need to generate energy, carbon neutral energy, which is we need to generate renewable energy, which is a carbon neutral. And for this, we need new and emerging technologies which can compete with it. For this, we need new technologies from photovoltaics to other things. So Bill Gates has now 2 missions after leaving the Microsoft as a full-time CEO. So he's working on a health and energy thing, and he needs a multi-billion-dollar investment on both this sector, health and energy. If you're more interested, I was also a member of a World Economic Forum Science Circle, so I was invited to write in a blog there. So if you're more interested to write about new type of a solar technology, you can go through this blog here and we did it. Today, renewable energy, most of them in photovoltaics, come from silicon. And silicon is a fantastic product. We like it. And thanks to our Asian countries, Asian colleagues, the price is so cheap that we are able to afford it for large scale deployment. It's a fantastic product. So we call them H1 generation, or which is a business as usual, which is a very good. And if you will look at the LCOE, levelized cost of electricity, in some part of the world, it's less than 20 cents watt per peak. So it's a fantastic product. It is a wide scale deployment. You can see there's also commercial product. It was a 3.5 here. 3.5 is a costly, but it has a niche application like building integrated, some niche application like satellite or in the city where the area is in high demand. Then in 1980s, thin film came to existence. And in then thin film, we have a CIGS, cadmium, indium, gallium solenoids. Since indium is very costly, you can replace indium with a copper, and that is called, zinc, and this is called casterite solar cells here. And now we all work with, this is the main theme of the conference today, is emerging photovoltaics. We call embryonic technology. Means this is working, the concept is working in the lab, it's fantastic, but in next 4 or 5 years or 10 years, it can go to the market because silicon is a fantastic product, but we believe that is not sufficient to fulfill the demand of our planet for a carbon neutral energy. And silicon is a fantastic product. Those emerging photovoltaics have many, many more newcomers. Let's say dye-sensitized solar cell is one of the oldest one, which was, of course, done by Nazaruddin, has done a lot of work there. Michael Gretzel, and this is the facade you can see in EPFL. This is an organic solar cell, flexible substrate. And this is a perovskite solar cell built in my lab. Here is a 10 by 10 centimeters. Then you have also catching up with quantum dot solar cells. There are new type of solar cells. We believe that either one of them is show the required stability of 25 years, the low cost, and they will go to the market. Just to give you flavor that why we need this one, the silicon is very cheap product, but you need 99.9999959 because the defect tolerance is not very high. So you need an ultra pure grade of a silicon. In case of our emerging photovoltaic, the defect tolerance is very high, and we don't need such a high purity quality in any of organic photovoltaics or perovskites solar cells. And the silicon, the thickness is 200 micron, 200 micron to harvest a light of 26.5% efficiency. But with the help of a perovskite, 400 nanometer to 500 nanometers can give you 25.5% efficiency. So almost same efficiency can be reached with the order of magnitude lower, 3 order of magnitude lower thickness. So if the thickness of the material is lower, what we will do, the price will cut down. Also, we don't need a very high scale annealing temperature, or we don't need high scale temperature on a semiconductor fabrication methods. So silicon was almost 6 decade old technology. It was first invented in a Bell lab in 1960s, and now at that time it was for a very niche application. The cost you can see was a $200 watt per peak, but now it's less than 20 cent watt per peak. So this has come a long way, many new concepts, many researchers has cut down the thickness, increased the efficiency, come with a new type of light management concept. And this all research contributed to the development of a silicon solar cell cell. And that is the market. If you look at the market share, this is a slide I took from the Fraunhofer. So how in 20 years before, we will, same in the case of mobile phone, 20 years before, nobody thought that we will have a smartphone in our hand. So 20 years before, no one knew that we will have so much of a wide PV technology deployment. You can see in 2000, year 2000, it was a very small. And now it's almost 133 gigawatt was installed in 2019. So this has seen an enormous, gigantic growth in the recent year, especially 2010, 2015, and this has been increasingly. But most of the market is belong to multi-crystalline silicon. Multi-crystalline silicon solar cell is cheap. They give you 16 to 18% efficiency. Monocrystalline are very efficient, but they are also costly. And thin film market is very less. 7.5 gigawatt thin film has been installed. And in this thin film, majority of them come from cadmium telluride, because cadmium telluride is a very successful product. And only one company, First Solar, make in America, is a very successful product. But we don't have enough resources to go for large scale deployment. And there's tellurium is only available to one company. So not other people, not other company can have about it. So most of them in thin film, we will see cadmium telluride, a 5.7 gigawatt, amorphous silicon, which maybe in 1980s was much more famous, is on calculator, on gadgets, 0.2 gigawatt. And some of them are also with CIGS technology, 1.6 gigawatt has been installed. The CIGS, in terms of a cost, LCOE cost, is difficult to compete with the silicon. So then people prefer to go to use the silicon solar cell here. So this is an NREL chart. NREL is National Renewable Energy Laboratory. We took from there and we plotted the emerging technologies and the efficiency. So this is a NREL chart. You can see Shockley-Kessler limits 33.6 here. So this is the thermodynamic limit a single junction solar cell can reach here. If you look at the OPV, I'm pretty sure today we have a great line of a speaker. 3 speaker will talk about OPV. So OPV is a papers you will see scientific literature. 19% efficiency have been published, but the certified is 17.4. Amorphous silicon you can see almost flat. There is no improvement. Similarly, dye-sensitized solar cells, the 14% efficiency paper have published, but the certified is 12.25%. Kestrite is also Now almost freeze is not shown any improvement in the last 5 years, as 12.6% has been certified. But you can see there is a rocket which is increasing. This is and seeing multiplying the factors. So you can see this is red curve. The red curve is continuously increasing, and because we were very fortunate, because the knowledge we gained from dye-sensitized solar cell and organic solar cells, we combined them, and all these community, both these dye-sensitized solar cell community and organic solar cells community, are now working on perovskite solar cells. And this the knowledge gained from both this previous has helped us to make a rapid progress. So now 25.5% NREL certified efficiency has been reported on a lab scale. And this is very fantastic, because 10 years back, we cannot think about there will be such technology which will be so efficient, which can absorb so light and convert into the electricity. So if you go back to the history, we'll give you a flavor. I am pretty sure Nazaruddin will give you. So this was the first invented perovskite solar cell as a replacement for a dye-sensitized solar cell, and give 3.9% efficiency. What somebody did in 2012, they replaced liquid electrolyte with a solid state electrolyte. And then it was a game changer, and from 10% to 25.5% in just less than a decade, 7-8 years. It has shown a jump, rapid progress. For any technology, for any product, what we need is a cost-effective, low cost. What you need to be a high stability, because silicon, when you buy them, they will give you a stability of 25 years. It's another story that they will die before. And you need high efficiency. So low cost and high efficiency will give you LCOE, levelized cost of electricity, on which a government tender will open. So all the technology compete within LCOE, levelized cost of electricity here. So if you give me, if we look at this scenario, a sky scenario from shell analysis recently. So the photovoltaics today is, photovoltaic today has a share, but this share is by 2070, it will be increased to very high share. It will be the main source of energy generation. 32% of our energy comes from photovoltaics. And if you look at the small chart, so how this will happen, so it will make in a rapid, in a sequential method. By 2025, we will be, by 2050, we will be having more than 25%, 2070, and by the end of the century, almost a 2/3 of energy will be generated by photovoltaic. So photovoltaic will capture the market. We just need a technology and system which can convert the light into electricity at a cost-effective price, because this is a carbon neutral energy. And I'm stressing the word carbon neutral energy. Then there's another term called energy payback time. So how much energy is used in making a technology? That's why we call energy payback time. So we'll look at this graph. The crystalline silicon, which is most efficient today, has the highest energy payback time. Maybe this graph can differ based on the location where you are. In Sweden and in south of Italy or south of Europe, Spain, south of Europe, it will be different because they have a more sun. So energy payback time will be different, but let's say that's just for a representative purpose. Crystalline silicon has the highest energy payback time. Then can polycrystalline silicon, then amorphous, cadmium telluride, OPV. And the lowest we can see is from perovskite solar cell, because the thickness is less and we don't need high temperature annealing. Let's say in titanium dioxide, to convert inert state to rutile, you anneal them at 500 degrees centigrade. This is a little bit high, but if you replace titanium dioxide with an SNO2, another very good N-type conductor, zinc oxide, or organics one, the energy payback time will be even less, because we just need to anneal them at 100 degrees centigrade. So energy payback time is very, very low. So thin film PV is ready to take off the market in filtration. And emerging solar cell, we don't want to compete with silicon. Silicon is a fantastic product, and we don't want to eat the share of the silicon. But it will be captured thin film market, and thin film market, due to government legalization, they will increase in the future. If we will calculate the LCOE is the lowest for perovskite solar cells. The silicon LCOE is not true, because the manufacturing cost of silicon is higher. So silicon LCOE is not true. Manufacturing cost is higher, but the cadmium telluride is the lowest LCOE, and we will compare with perovskite solar cells. It will be even lower because less thickness here. NREL has calculated the true cost of ownership at less than 20 watt per peak as compared to 45 to cadmium telluride, because cadmium telluride is the lowest. Why is it all happen? Because we are using very less material and low cost processing method. We don't need a high-tech semiconductor methods. And also one thing is that the silicon absorb in near infrared region, And perovskite and all these third generation solar cells, we are absorbed visibly. We can see the colors. So we absorb in the visible part of the spectrum. So this is also good for making a tandem devices. So some of the companies which are working on to making a tandem of silicon with perovskite, CIGS with perovskite, and but on the other hand, silicon and CIGS, they are very stable product, and perovskite, we are trying to reach those numbers to be stable. If we go in the more electrical properties, the losses, why these solar cells work well. So the losses in case of perovskite solar cells is at par with the gallium arsenide or silicon solar cell. There's very less losses, because thickness is less, so that the charge is extracting and travel to the electrode before being dying. So gallium arsenide, silicon, CIGS. So perovskite has also even lower. If you take the standard methylammonium lead triiodide, it's a band gap of 1.55, and we can get a 1.15 VOC. So the loss is very less. Even some people has reported even higher value and lower losses. You can go to 0.35 electron volt losses, very low slabs. So this is another chart that how we make a progress. This is a recent review article. You can follow from there if you're more interested. How the progress has been made from 3.8%, which I told you, and where they were using a dye sensitized solar cell. It was a liquid electrolyte, so the device lasted for only a few minutes. People did the research, they forget it. But again, they came back in 2012, the idea of replacing liquid electrolyte with a p-type solid state conductor, because organic chemistry and organic semiconductor, there are plenty of them now which we are using it. And today also someone is going to talk about p-type semiconductors as a whole transport material. So we replace them, and then the efficiency has rose up. And with the help of compositional engineering, with the help of new material, new ETM, new device architectures, the efficiency has completely rose from 10% to 16% and 25.5% this year. With the new composition is 95. So compositional engineering has helped a lot, because this way you can modulate the absorption onset. If you modulate the absorption onset, you modulate the current, because the higher the absorption, the higher the current will be translated. And this 95, FA95 and MEPBR3 5% is the best one, which is giving a 25.5% efficiency. So maybe for photovoltaics, but not, but those who are the new students like here and who are going into the field, that's what I'm talking about, only efficiency, what this term is called. So this is, we call it a figure of merit for the photovoltaic devices. This is a normal JV curve here. And we have an open circuit voltage, the current here, and the fill factors. If you multiply with VOC and the current, short circuit current and fill factor with the intensity of the light, you will, we call it a power conversion efficiency, or solar to electric conversion efficiency. That's why we always call the term efficiency. And in ideal case, the devices in the dark should have a zero current. So it means the devices are not having any recombination issue. They are not suffering from it. If you are more interested, we will explain you more in the detail here. So again, what is the good thing about a device should be, photovoltaic devices should be a very efficient charge separation, and the extraction of carrier should be also very efficient. What we don't want is recombination. We don't want electron and hole to recombine. It happens. We cannot remove it, but we want to slow down it. We want to change this, and contact resistance between the interface. So the contact resistance at the interface lowers the device efficiency. The recombination in the inside of a devices lower the efficiency. But what we want is a very good efficient charge separation and extraction of a carrier. So if you have the perovskite solar cell will work, if you look for the perovskite is a light absorber. They absorb the light and generate electron and hole pair. So the electron goes from valence band to conduction band here and inject into the TiO2. So the arrow, which is the full arrow, you can see this is a desirable process. The dotted arrow is undesirable process. So this dotted arrow is undesirable process, which is like a recombination. We don't want electron to go back to the HTM side or cathode side. They get recombined. So we don't want it. So the current we can modulate by designing new absorber or by compositional engineering. While the VOC, which is also very, very important, open circuit voltage, this we can do by defect passivation. This is also has been done in the silicon. Now we are doing it, and also the community has seen a very good jump in the efficiency. So we passivate the defect, we passivate the grain boundaries. We can also change the orientation, interfacial ordering, which is another thing working heavily on layered perovskite. Energy level of charge selective contact, because perovskite is sandwiched between an N-type conductor and P-type conductor. and both should be very well aligned. So energetically, they should be favorable to inject the charge in a facile manner. Otherwise, they will be not energetically aligned, and we will have a loss at the interfaces. And bulk properties are effectively controlled by the interface. So the type of the crystal, the size of the crystals, this contribute a lot to the open circuit voltage, and surface passivation to passivate the grain boundaries or make the crystal larger to minimize the grain boundaries. So in this way, we will minimize defects and we can have a higher VOC there. What my laboratory is working on, all this phenomenon, all this type of problems in the solar cell, perovskite solar cells, we do compositional and interface engineering. We change the composition of active material, that is perovskite. We modify the interface by placing in new materials there, which is energetically favorable. Sorry, like 2D materials. Now we are thinking beyond graphene, the 2D materials here. Surface passivations, there are many modulator or passivating agents. We are using it to minimize the, to passivate the surface to fill the grain boundaries. Hydrophobic encapsulant, not about mechanical encapsulant, but molecular encapsulants. There are some materials available which are which can encapsulate the surface biomaterial things. Hydrophobic dopant for HTM. HTM we call is whole transport material, is the P-type material, but the most of them require doping, and doping is from lithium salt. This is a trade-off. So we developed some ionic liquid-based dopant, which doesn't compromise on the stability and the stability of the devices while giving the same performance here. And we also interested in designing of in a whole transport material, P-type material. So P-type material, as I said, is very good for as a whole transport material in our organic solar cells here, in our perovskite solar cell. So this is the cartoon of the devices, and you can see as the layers are, they have a 3-4 layer. This is the perovskite layer, which is a sandwich between an N-type layer. N-type layer is generally titanium dioxide. We also take this as a tin oxide. You can also take zinc oxide or PCBM, and then you have a whole transport material. Perovskite absorb the light, and then it generate electron and hole pair, which travel to their respective electrodes to get collected. So most of them is HTM is a spiro, but Samana will today talk about new type of spiros, which can be more, new type of HTM, which can be more effective. This is a cross-section diagram of a cartoon of a devices. So you can see the thickness is exactly, it mimic the cartoon. This is the devices, and this is the perovskite. It absorbs the light and goes to the whole transport layer as a thinner layer. ETM is also a thin layer, and this is an FTO. So there are different type of architect also possible. The mesoporous, when we take titanium, when you take titanium dioxide, we call NIP. This is the most efficient device configuration, which give you 25% here. You can even get rid of mesoporous. You can take titanium, tin oxide or zinc oxide. So you have a normal NIP structure. The efficiency is also 25% reported. Most of the people who come from organic solar cell background, they prefer inverted configuration more because they are more comfortable. And PIN is also less hysteresis there because thickness is much less there. So PIN is inverted configuration. So first you have a HTM, then you have a perovskite, then ETM, and then you take a contact here. So 25% has been also reported for inverted configuration in the tape of the. When we started to work in 2012, one of the few groups there, we also started with the normal methyl ammonium lead triiodide. So you can see the normal methyl ammonium lead triiodide is here. The crystals very small, number of grains they're higher. With time, what we did, we also learned, we evolve ourselves, and always the interest is to make the crystals larger. So now we take a composition of a cocktail. So this is formaldinium iodide. Then we have a methyl ammonium bromide for higher voltage and lead iodide. So when we took a cocktail, we can see the crystals are larger. Now even we will getting much larger crystals, just for a representation, and the grain boundaries are less. And you can see we have a jump in both current as well as the voltage. Similarly, what we were working on methyl ammonium, then we shift on the formaldinium because formaldinium is 1 CH2 group extra, ionic radius is a little bit higher. So you can change the composition, and by changing the composition, you very manually, very systematically, you change the band gap of the material. And also formaldinium, you can see is a higher band offset here. So this was a very old study. We did is a 60-40 ratio of formaldinium, 40%, methyl ammonium 60. You can see the crystals are here. If you will completely replace iodine with bromide, you have also yellow color of devices, bromide based, which is good for building integrated photovoltaic applications because they are transparent. There are also some group of thoughts, which are groups of researchers who are working on evaporation, on sublimation of perovskite. There are plenty of them. This is also very good. There are two ways of deposition. What we do generally on a solution processing route, but there are also groups, very good groups there, which are working on thermal evaporation. And they've also reported very good efficiency. The good thing about thermal evaporation is that you can control the thickness to a nanometer range, because then there is a quartz crystal microbalances associated with it, and you can precisely control the thickness to a nanometer range. In our case, we don't control in wet chemistry process. We are always 5 nanometer or 10 nanometer plus or minus, even we use the same composition or same reference. So just to give you an idea how the microstructure changes here, this I borrow from a recent review article or perspective here. The solution process give you large crystal, in the case of methyl ammonium, while in thermally operated, the crystals are smaller there. It's a triple cation, we call cesium, methyl ammonium, and formaldinium case here. And in case of evaporation, this is the crystals in the case of evaporation are always smaller. And that's why the highest efficiency is always reported from a solution process method, because the crystal are larger. But the good thing about evaporation is you can precisely control the thickness of the material for reproducibility. So the current challenge in the perovskite solar cells is the stability. And the stability comes from not one of the two things, apart from perovskite, which is salt, which degrade in the presence of oxygen and convert back. There is also something unfavorable. This perovskite is just convert from methyl ammonium. You take it, so it produces free radical. PBI2, PBI2 again form HI, hydrogen iodide, but also the titanium dioxide, because titanium dioxide is a photocatalyst. So in presence of light, it produces UV radical, and it goes titanium 4 plus, get to the perovskite, and even accelerate the degradation of perovskite. So that's why we are now working more on using tin oxide, and this is we believe is doing a good result for us, and we are happy with that. Let's talk about now. This was some of them layered three-dimensional perovskite we talk about. Now another find the term is called layered perovskite. He called two-dimensional perovskite, but I call them layered perovskite. They were the pioneer in this field, and they did. So what we took is you can take some pentafluoromethyl ammonium molecule, pentafluoromethyl ammonium iodide, and we will, because they will not form a three-dimensional structure, and they will form a layered perovskite. So what we call is a bilayer type of perovskites. And what we recently, what we did is we take fluorinated and non-fluorinated molecules, because fluorine we know as the surface tension is very high. They make the surface hydrophobic, or you say ultra hydrophobic, and we deposit a layer after annealing the 3D perovskite, and this is called bilayer perovskite. And the absorption onset was similarly changed. So the materials, there was a no change we can see in absorption onset in both this material with fluorinated or unfluorinated. Sorry. And also it formed PBI4. If you take off pentaethylamine lead profile, it formed PBI4, and in case of fluoropentaethylamine, it formed a layered perovskite. So these are indication that it formed a layered perovskite here. But what we do is, if you will see in the surface, the topography, how it changes. This is the pristine perovskite, a three-dimensional. Let's say mixed perovskite, or this one. On top of it, we will do it FPA molecule in different concentration. The surface changes, you can see differently. And in case of PA, you can say the crystals are not like that, but it form a lamellar type of a structure. But what the significant change you will see, it's here. This was the aim, to make the surface more hydrophobic. The pristine perovskite here, in case of mixed perovskite, they give you as a contact angle 78. With the PA molecule is 94, and with the fluorinated is 99 degree. So the surface became more and more hydrophobic, ultra hydrophobic surface. So this ultra hydrophobic induced in the bilayer perovskite will allow us to make the device more stable. I think many people has published extensively on this one. Even they do 1,000 hours of MPP tracking, as has been reported. In our case, we is also improved the efficiency with the pristine perovskite, give you 17.6%. But this bilayer perovskite is close to a 20.6% or close to 21% efficiency. These are also giving. So if we will look at this JV curve, this red curve is a fluorinated molecule, followed by a blue curve, ethyl ammonium iodide, and the pristine is here. And always we have a significant change in the increase in the voltage. So voltage is 70 millivolt higher. and voltage is 70 millivolts. Current is similar, so you cannot see improvement in the current here. This is a cross-sectional diagram of a bilayer perovskite structure. So this is a tin oxide, there's a perovskite, and then you have a very thin layer. You can see it's buried between. Here is a thin layer of PA molecule, and this is a thin layer of PA molecule. So what we did, we deposit a PA molecule, pentafluoromethyl molecule, FPA molecule on top of 3D. So we were also very interested because both these molecules giving different properties, different electro-optical properties. So we were very interested to learn their behavior, how they are oriented this way. And we collaborated with some people who was very good in different spectroscopic technique. And we see both these molecules have a different orientation on the surface. Like you will see, and we calculated from the stretching band of NH3 and here, and this gives you a different value. So in case of PA, it lies flat with the perovskite surface, while the FPA is perpendicular to the surface here. And that's why this different orientation of the molecule sitting on the perovskite give you a different electro-optical properties. Let's go down later. I think I'm running out of time. So another molecule we did log back with collaboration with Nazaruddin also is using an imidazolium iodide, because iodine ion migration is very common in perovskite solar cells. To fulfill this, we have used imidazolium iodide as a reservoir, and we passivate the surface. A very thin layer of imidazolium iodide was placed on top of it, and that time also we have increased. We have seen a jump in the efficiency from 18.6 to 19 point, almost 20% efficiency, I think 3 years back here. Then another molecule we were working on, thiazolium iodide. This was also, we were working parallelly, and during our submission of paper, we received feedback from referees that, oh, there's another paper. So it was from Krathaji's group on using thiazolium iodide. And they use as a 1D layer. They call it after depositing perovskite, they use as a 1D layer on, and they reported a very good efficiency enhancement with this thiazolium iodide. And stability enhancement here is a very good, and they are much more stable here. In the meantime, we were also working in the parallelly. In thiazolium iodide, why we choose, because its energetic level was 5.55 electron volt, 5.41 and 5.23, very well favorable to the conduction band of the perovskite. You can see and the best one was 5.41, and that's why the MIC3 give the highest value, because it was more favorable. And also the devices, we put a very thin layer of thiazolium iodide on top of methylammonium tetraiodide by spin coating process. This is an IPC graph, and how much a photon is converting into electrons. So these also give a little bit higher voltage of increases. And what we did admittance spectroscopy to know the defect of passivation. So we find that that's this thiazolium iodide treatment. Well, what we did is increase the depletion length. If you increase the depletion length, you have a higher voltage, and the built-in potential was a little bit higher. And then we also defect the defect densities values. So these type of electrical parameters we elucidated with the use of thiazolium iodide, and they all suggest that the electrical performance has been increased. The defect density is lower, the activation energy is higher. Similarly, we are also using, recently we are doing NBS. NBS is very good because it oxidizes and it produces free radicals. So instead of iodine, it will be bromide, which will passivate the surface. And there's always unreacted lead on the surface. So the unreacted lead can react with excess of halide, NBS or imidazolium iodide, and will form and unreacted will combine with lead iodide. So this also we have used NBS recently. This is also working slightly from 17% to we go to 18.2%. They were also increasing the stability. The last work I want to show about is we are thinking beyond graphene, because many things have been reported for the graphene. And we are thinking beyond graphene of using 2D material as an interfacial layer. They are not like active like molecular like NBS or imidazolium iodide or layered perovskite, but they increase the stability to a significant extent. So we are working on MOS2. We have worked on, you can see MOS2 very uniform solution, no gel, no aggregation, and the absorption it doesn't also compete with this whole transport material, perovskite material. This is a no unfolding in the transmission spectra. We can see it in the TM spectra. And we deposited a layer, and the layer thickness was less than 5 nanometer. We calculated it, and absorption on top of the perovskite also doesn't change. There's similar absorption it's on it. And we place a thin layer of MOS2 and as an interfacial layer between the HTM and the perovskite. What we did, you can see that it's VOC, because the energetic level was is not favorable between triple cation perovskite and PTA. So by placing MOS2 2D layer, it's energetically favorable, and we have a significant boost in the VOC open circuit voltage. And from 15 point we got to 18.53% we reported. So by placing MOS2 layer, we can engineering the interface. And the good thing is why this DOP and PTA was a DOP and free. So DOP and free devices always give you less efficiency, but they are more stable. So we use a DOP and free polytroy PTA, but we use an MOS2 layer on to increase the performance. And what we noted is a reduced tap density and the interfacial losses were lower. And there were low energy required for trapping and detrapping of charges, which provide extraction of more efficient photogenic charges. The device also gave a higher voltage, a higher performance, higher stability. You will see if you look at the maximum power point tracking of the devices with 2D MS2, 2D as the interfacial layer give a higher performance. As a contact angle, you will see with the placement it has increased.
2 minutes time, please try to wrap.
Okay. Yeah. Thank you. Thank you. So this is an FTO surface on deposit with the tin oxide. This is a perovskite, and this is a perovskite with 2DMS2 here. This is a cross-section diagram of a device as we have seen it. And if you're more interested to go, we have to run it. It's a defect density and interfacial defect. We calculated it. And built-in potential is always higher with the placement because it was energetically more aligned. The depletion length has increased a little bit, and trap density values, which are very good, is also lower. Trap density is also lower. And another is, if you're more interested, it's sorry, we go that here. Yeah, so this was the layered perovskite. And pure layered perovskite is also many people are working, but pure layered perovskite has a problem with the quantum well is very, very high. The quantum well is very, very high. The charges are not very efficiently to migrate. So what we adopted is butylamine, which we doped with the lithium. So with a pure layered perovskite give you 9.95%. With doping, we were able to minimize the quantum well. We minimize it, and we seen a jump in efficiency. So in pure perovskite, the Finney areas are difficult to generate, and by doping we can lower the density of acceptor type and trap state, and then the charges can go higher. So you can follow this one here. There's another two-dimensional perovskite is Dan-Jacobson. Here also, what we saw is before it was the RP phase, and Dan-Jacobson is is another very good perovskite here in the layered perovskite category. By placing different organic groups here, you can have plenty of opportunity to design new type of DJ phase perovskite. And this efficiency in the red curve you can see is also increasing to 18%. These are much more stable perovskite than the three-dimensional perovskite. The recent work is we are also working on FA, because FA has a more higher onset. And also there's no phase transition. Methyl ammonium has a phase transition from at 85 degrees centigrade. It's a very low temperature. There's no phase transition. So we are working on FA powder pre-synthesized, and we have achieved improving performance in the photovoltaic diffusences. This is the last slide. Let me show you with this with the use of a polymers, a PVDF, because the polymers also can increase their stability. But here, by purpose, we choose a very thin thickness of 150 nanometer of perovskite for other application like BIPV, and we put a polymers, we deposit a polymer on top of it to encapsulate the devices and to increase the stability. PVDF is a dielectric polymers, which we observe increase the efficiency as well as the device performance was very much increased there. So just as I said, is the running out of time. So I will summarize it. That's perovskite is a blockbuster technology in thin film PV. In terms of efficiency, we have seen a rapid progress and huge cells there. By molecular engineering, by different introduction of a special layer at the perovskite STM interface, a special layer with many, or we call them layered perovskite, or we call them what is to boost the efficiency is a very good strategy here. A special layer, especially fluorinated molecules are ultra hydrophobic because the surface tension is very high in fluorinated molecules. They are ultra hydrophobic, and perforated benzene moiety can induce more stability here. 2D material also increase the stability, but they are inactive in terms of molecular exchange, but they in terms of stability and band gap alignment is very good here. This is the very good things about perovskites here. The price competition with mature technology is again a challenge. I think not the numbers, not the stability, because silicon is very low. So the price competition with mature technology will provide the market entry of any new emerging solar cells, because there are other concepts. And the lifetime and governmental support in this type of technology. Governmental support means the use of lead, sometimes they call it, or the use of other thing. So it's very, very necessary here. So with this, I like to stop here, and thank you very much for listening to me and my financial support for the ERC and the Spanish government.